Thanks for having me to the conference. My name is Dr. Chin. My co-author is Mr. Kai Yuan Chia and Dr. Simon C. Today I'm going to present the title on Deep Transfer Learning Application for Intelligent Marine Debris Detections. As you know, that trash in ocean is causing harm to the marine environments. The current most used removal techniques is the use of trawlers. And it's very highly laborious jobs and require high cost as well. So with the use of AUV, which is autonomous underwater vehicles, removing marine debris could be one of the best and most reasonable price solution available. So this paper will focus on a sensor system which allow the AUV to see and understand the surrounding environments. One of the way the AUV can see their surrounding is through the computer visions and machine learnings. So AUV are unmanned and self-propelled vehicle. As you can see, there's no need for any human being to actually operate it, but sometimes you will need to have a tethers to provide the power supply and also to have some more robust communications. So by having a built-in AIs or artificial intelligence, the system can actually recognize the debris and quadratic life in the ocean if needed. So it's possible to deploy multiple AUV in the oceans, efficiently removing the marine debris in the environment, not just one AUV but many AUVs. But this paper we just emphasize on just one AUVs, and it basically try to evaluate the use of the "You Only Live Once" version 5 small. This acronym is called the YOLO V5S to compare with other network used to identify the marine debris. So the YOLO V5 can detect object much faster and work in the real time than other neural networks such as the regional convolution neural networks, despite the higher mean average precisions. And it's also very important for AUV as the marine debris might just shift away from its field of vision due to the wave, and before it's being detected that the debris should be removed. Not going through all these different approach, there's a YOLO V2, V3 and so on, there's tiny YOLO and faster RCN and SSD. Each of them have their own merit and basically the pros and cons. So what I try to look at is YOLO V5S networks for underwater marine debris, and the data set that is not collected by us, but we just use the some of data set that's being available by University of Minnesota Robotics Labs. And you can see that this is things that you can actually try to look at this trash can 1.0 and instant segmentation labeled data set of the trash observations. So you can just download the data set, and just to give you some information on this trash can data set, it comprises donated image that is 7,212 images currently, which contain the observations of trash, AUVs and a wide variety of undersea flora and so this is citations. Alright, so the data split, you can see there's a material version of trash can because trash can can made from different materials, and also there's animals as well, and there's an instant version of trash can. You can look at all these informations, and the blue one, the red ones, or the pink one is just the data split between the training and validations. So validation is always less as compared to the training data set. As I mentioned, there's 7,212 image. We extract 1,000 these images that we use for model into the new folders. That you can see that these are all the data set that we can actually download. So you can see we just use 1,000 these images because of our constraint in our laptops. But you can see after you download the files, so I save it, 1,000 extracted these images. As you know that we are using the RoboFlow. Okay, this is one of software that we can do a lot of intonations. So we just try to upload these extracted images in the folders, and these files JSONs which consists of these intonations into the RoboFlow, and we just drag and drop into this and we press upload buttons. You can also try to edit the image intonations, and then we can combine into a similar size portions and we upload to the online image tools, and it's called RoboFlows, as you can see from here. You can also try to, as you can see that we try to trim the intonation if you want to. You can see that's one of the images of 1,000s. That is just a samples, and we can do a final uploading, but we can also try finish uploading for the final uploads, and the interface will prompt you how the image could be split, so we can split this image into from 1700 for training, validation 200, and the test set is 100, so total is 1000. And it will take a few minutes for that to happen. Uploading, and we have the pre-processing and the augmentations. So there's columns that we can, or the functions we can actually do a pre-processing, okay, and we also can do the augmentation. For pre-processing, we try to resize to a slightly small 416 times 416 pixel, for which is a smaller size as I mentioned, flick to a faster training, and we use a different augmentation approach to try to increase the number of this image for. So we try to export the custom data set. So after we have done that, okay, so you will see that we try to increase from 1000 to 2001 after we do the augmentations, and then we try to export into the download codes, so with YOLO 5S v5 formats, and this code we use later on the scripting of this model. You can see from the left hand side we have this. We can press the start training using the RoboFlow functions, but we do not have that function because we are using this for free. So we have to export this as a YOLO v5 PyTorch. You can choose different one that you want to use, but we use the v5 PyTorch and we download the codes. Okay, so you have copy and paste the code somewhere so that we can use it later on. For training wise, we use Google Colabs. It's used to train the YOLO v5S model, and the GPU that we provided was NVIDIA Tesla P100 PCIe 16 gigs. So I believe that you are very familiar with this kind of configuration that we have done. Parameter of YOLO v5S model can be changed here, and evaluations of this model. So there's an intersection over the unions. That's something that we use. Alright, and this is basically intersection over union is used to measure the performance of the predicted bounding box. So you can see that the numerators, the B box predicted and the B box ground true are the area under the curve for predicted, this ground true bounding box respectively. So we try to expect a bit higher value for this one. And the next one is mean average precisions. We try to evaluate how often the network can recognize the four classes in the group of images. In short, is NAP work based on the average precision at different recall values. So just to refresh, the true positive TP is at the numerators. It's outcome where the model correctly predict the positive class, as well as the false positive showed an outcome where the model incorrectly predict the positive class. So this TP plus FP will be at the denominators. So again, this must be the very high values that is what we want to achieve. So the recall reflect the ratio between the true positive and actual positive. Alright, so the negative is outcome that the model incorrectly predict the negative class. So this is the false negative. So therefore the MAP can obtain by generating a precision recall curve using the IOU and integrating this curve, and which is something that we can do that. As for the result, the Poco pre-trained YOLO v5S weight are then specified for training. The training took place on a Tesla P100 GPU, achieving MAP 0.5, which is the mean average precision of 0.896 for the validation set on the 150 epoch. So it shows a steep rise in MAP at the start while stabilizing at the end as the learning rate decay starts to prevent overfitting. The validation loss and the MAP graph are used to evaluate the training process and to determine if the model is overfit or insufficiently trained. The MAP and the loss value started greater at a very certain number of epochs, and overfitting did not occur, which indicate an appropriate training durations. So once we finish the trainings, the final weight at 150 epoch were then exported PyTorch format. Then we train the YOLO v5S weights, evaluated based on the test data set with an example predictions as shown in the image. So after the evaluations, the YOLO v5S achieved a test MAP 0.5 score of 91.2% and an inference speed of approximately 4.1 millisecond per image for the test set. So you can see that the YOLO 5S, the ground truth is on the left hand side and the predictions is on the right, which is around 0.9. And for the other results, the AP 0.5, the average precisions at the IOU threshold of 0.5 score for each class were then evaluated as shown here. On the right hand side, you will see that the Euro V5 models attain a high AP 0.5 score for all classes, which includes the shells, starfish, trash, and animals, etc., fabrics, rubber, and papers. Overall, the trained Euro V5S model was able to generate a very high number of true positive prediction across all classes, as you can see. Among all the classes, the rubber and the paper class, which you can see from here, the rubber and the paper class, paper and the rubber, achieve nearly 100% of true positive prediction, as shown in the confusion matrix on the right hand side. The shell and the, which is here, class achieved the lowest percentage of true positive predictions of around 75% and 77% respectively. You can also observe that the trash, the class has a widest range of false positive and the false negative predictions. So this would mean that the trash class, which in this case the trash, is easily confused by the Euro V5S model with other classes during inference. So this is actually expected, as many possible objects can belong to the trash class, and it's difficult to accurately train the model to predict all the possibilities. So the next, we compare with other models. As you can see from here, the Euro V5S, Tiny Euro V4, V3, Retina Net, and faster RCN. The MAP 0.5 values are the MAP 0.5 scores achieved by the trained model when performing on the test data set. The Euro V5S achieved the highest test result of 0.912, followed by the Tiny Euro V4 coming as a second with this value of 0.874. Whereas for the faster RCN model has a slightly lower MAP 0.5 of 0.808, despite being a two-stage detection networks. For Euro V3, it scored the lowest of 0.7, and this MAP 0.5 metric is actually used to evaluate the accuracy of model, with higher the NAP 0.5 representing the higher accuracies. So you can see that the most accurate of the 5 models, the IOU threshold of 0.5, you can see Euro V5S performed the best. And in terms of inference speeds, 4 and V3 is 3.1 millisecond and 3.3 millisecond respectively. Euro 5S is slightly longer due to its slight complexity, and whereas for ReadNet and fast RCNN has a slightly slower inference speed of more, which is 53 milliseconds and 54 milliseconds. So you can see that the Euro V5S and V4 and V3 are quite suitable for deployment on the small device, due to the fast inference speeds. And because of these deployments on an AUVs, the object detection network must be fast, lightweight, and utilize minimum processing power simultaneously. So a smaller AUV may only have a space for smaller processing unit, so we need to make sure that we have something that is fast in the speed, as well as the size in terms of the weight itself. It has to be small. So you can see that the model weight, after we export in terms of megabytes, you will find that the Euro V5S weight have the smaller size, as followed by the Euro V4, which is having a size of 22.5 megabytes. So this indicates that the Euro network are better suited for deployments. So as for the deployments, which is the next phase, we actually use the Android Studio along with the Android SDK, which is a software development kit. Firstly, the YOLO V5S model was converted to the TensorFlow Lite, which is very useful if you want to do any deployments in this kind of format. And it also allowed the Android deployment using the TensorFlow Lite frameworks. So these actually convert this YOLO V5S TF Lite FP16 format, and which has a size of only 13.87 megabytes. So the code for the Android applications was written in Android Studio as mentioned, and is based on the official TensorFlow Android object detection examples. So you can see that this model, the YOLO V5S model, we imported into Android projects and we built via the virus debugging approach, and then we will be testing this on the video footage from the Gentek JEDI dataset, and the average inference time was about 50 to 80 milliseconds on the Poco X3 Pro Android device with the Qualcomm the Android knows the 640 GPUs. So this speed is approximately about 12.5 to 20 frame per second. So the application performance varies greatly across different devices, and that also depending on the GPU of the device. So there's always an options to configure the applications to run on CPU or GPUs, and the CPU result in a slower inference speed of 360 to 400 milliseconds on the Poco X3 Pro, and which translates to approximately 2.5 to 2.7 frame per second. The hyper Dolphin AUVs is used to capture the image and the video footage of the JEDI dataset. Has a maximum forward speed of 3 knots, around 1.54 millimeter per second. And similarly, if we use the AUV, it moves across the seabed at an average speed of 1.5 to 2 meter per second in the straight lines for surveying. Okay, so this means that the Android application could be able to process a range of between 8.33 to 10 frame per meters of the seabed based on detection range of 12.5 to 20 frame per second. So in conclusions, what we want to conclude of our work in this paper is that we have developed and evaluated the performance of 5 object detection networks for marine debris detections on board the AUVs, and we have concluded that the YOLO V5S model was best suited for underwater marine debris detections due to its high accuracy, speed and size. And we have actually deployed on the Poco X3 Pro, demonstrating a decent descent speed of 12.5 to 20 frame per second with a high accuracy score up to 91.2%. The object detection network can also be trained to perform other functions such as hull inspections and ship navigation instead of object detections. So with that, we can actually program to process images as specific intervals, and we can also tag to a geolocation data as well, and this information can then be evaluated to identify location of higher concentration of marine debris. So these are something that we can add on, and we also will try to do in the future works to use the geotagging algorithms to assign latitude and longitude data to the predicted image. So with that, thank you very much.